Right, welcome to my talk about using ScyllaDB for distribution of game assets in Unreal Engine. My name is Joakim Lindqvist. I'm a senior tools programmer at Epic Games. So I'm going to talk about Unreal Engine today. And Unreal Engine is software used to make computer games, pre-visualization in movies, TV shows, architecture, automotive. Pretty much if there's anything that you can do like real-time 3D, there's a fairly good chance that Unreal Engine is used for it. And for a lot of the games that you might play on, like say PlayStation, PC, Xbox, a lot of those games do use Unreal Engine as their engine of choice. And Epic, outside of sort of selling Unreal Engine, we actually make games ourselves. The most known one is probably Fortnite, and that ships on a bunch of different platforms, ships super frequently, actually uses a lot of the features we had into the engine. So it sort of acts as a bit of a test bed for us on top of being, a super large game. And so we've been using all of this technology that I'm talking about today to ship Fortnite and a bunch of other stuff that we've been doing. But so what I'm going to talk about today is, first of all, I'm going to give you a bit of like an introduction into how it's like building games, because I assume most people don't really know what actually goes into it. And then I'm going to talk a bit more about the technology we built called Unreal Cloud EDC and how that uses Scylla. And then I'm going to end talking about some of the future stuff we want to do using both Unreal Cloud EDC and Scylla. But so let's start by talking about what it actually goes into building games. So games is a fairly complicated piece of software. There's two things that goes into it. The first part is like the typical software part of source code. The source code is both used in the game itself, in the runtime, where that goes onto the disk where the game is. And then there's also a bunch of tools surrounding it, like the Unreal Editor and a bunch of other things that you're going to need. But outside of the source code and typical software stuff, there's also game assets that are essentially data that you display in the game. And these can vary what they actually are. They can be like a mesh, a 3D model. It can be a texture, which is like a description of the surface of the object. It could be sound, music. It could be like a super specialized kind of asset, like a particle system. So lots of different things. And the size of each asset can vary quite a lot as well. They can be a couple of kilobytes and they can be multiple gigabytes. So varying types of data, but we need to sort of have all of these available to us to be able to sort of play the game. On top of all of these sort of large assets, it actually takes quite a bit of time to build an asset as well. So we typically have a fairly large team working on building assets. So it's not unusual for a game when it's close to sort of its final stage in full production, where to have more than 500 people working on building assets onto the game itself. So a fairly large team, and then to find the kind of people that you need to build that. Because it's a fairly specialized skill, you tend to end up being spread out all across the world. You'll have a bunch of different offices in a bunch of different places. So these assets, not only are they large, but they also need to be available in a bunch of different places. So just to sort of give you an example of what people sort of spend their time on when they're sort of what it looks like when they're building the game, this is a screenshot of the Unreal Editor that people work with. So you can see, I think this is the level editor. You can see like a 3D scene there. And then to the right, you can see some assets like the lemon that's highlighted. And the lemon is actually not one asset, it's actually multiple assets. So it's like the 3D mesh of the lemon, textures, probably multiple textures and shaders. And there's a lot of things that goes into it. And you can see the 3D scene here. There's just a bunch of stuff in there, right? So there's just so many different things that is inside one single sort of scene in a game. And then you can see, probably recognize this if you've tried to use like Blender or Maya or some 3D tool like that. It's sort of similar to that in how it looks, but this is just one view in the editor. There's a bunch of other ones where you can look at, you can produce your own audio or a bunch of different other things. So, it's a big software that does a bunch of different things. But the data that we see here, it's like once you download this texture or something like that, that's not in a format where the editor could just present that to you. So it needs to do some transformation of that data. And that transformation is part of a process that we call cooking. So it varies from asset to asset exactly what kind of transformation that needs to happen. It could be a conversion of file formats. It could be compression. It could be compilation. It really varies. But the sort of common thing across all assets is that they are cooked, or a lot of them are cooked. And the reason for this is like when we share assets between each other, they're submitted into source control, right? So they will be you will get them through source control, but they will not be in the perfect format that you want to use. They will be in some sort of looseless format that is like the best quality you would ever want to use in a game, and then we need to apply these conversions to them to make them into a runtime compatible format. And it can actually take quite a long time to do all of this conversion. If you haven't cooked anything before and you're going to sort of cook a game, that could take as much as 24 hours to cook the entire game, which would just be completely crazy. You couldn't really work with that. So what we do is apply a caching on top of this called the DDC, the derived data cache. And the idea with this derived data cache is just contain a copy of all of the data that you cooked before, so that if you go to cook it again, you can just fetch it from the DDC instead. But that local DDC is not the only caching layer we have. We also typically have like a shared cache, and that historically used to rely on on-premise network file shares. So essentially, when I cooked an asset, I would upload that to the filer, and someone else in my office would be able to download that, so they didn't need to cook it again. So that worked quite okay. I mean, there's problems with filers. They can be a bit slow when lots of people hit them. There's just, you need to set them up. There's lots of sort of headaches when it comes to scale up and so on. But it worked okay. But now sort of we've talked about sort of how we're sort of geo-distributed in a bunch of different offices. So these are like per office, right? And while it worked okay, we're starting to see, like, you see more offices popping up more quickly, contractors spinning up for a couple of weeks work, those kinds of things. There's just such an overhead in managing these. And then, of course, we saw a trend even before the pandemic with people sort of working more from home, being more remote and so on. But then with the pandemic, this just became such a much bigger problem, where people are just working from home and they need infrastructure that can work for them, even though they're not in the same physical building as everyone else. So we tried to solve that by using our VPNs, but that just doesn't work. It's too slow, and there's just too much data that goes over this VPN that bottlenecks the VPN proxy and so on. So that didn't really work. So what we figured out, what we need is another layer on our caching system that is built for the cloud, that is geo-replicated, that can just feed everyone all of the data that they need on top of these other layers that we have from the past. So we decided to build something called Unreal Cloud DDC to support exactly this. And the idea, I mean, it's fairly self-describing what it is, right? It's for Unreal. It's a DDC that is built to run in the cloud. So yeah, it was about a year ago that we sort of rolled this out, and it's been doing quite well. So this is sort of our solution to that problem of distributing all of these assets across the world. But so let's look at what we actually store in the DDC. We store sort of cache records that are in a format called compact binary. So that's a self-describing binary format. So think of it sort of like a JSON file, or more accurately like a Bison file. So it's a binary serialized self-describing format. So you can see like an example here to the right where you see like a couple of different types of fields. The major thing that we add, on top of being really compact in terms of serialization, is a type called attachments. So an attachment means that you have that object, but then that's also like a handle to some other thing that is related to the object. Logically, they're part of the same thing, but it's something that you can fetch if you need it. And you can see the attachment field there and the hash. And the way we reference these attachments is by content addressing them. So that means that we take the hash of the content and use as the identifier of the content. This is a fairly common scheme you see in a bunch of different things. Git is perhaps a most famous example of it. But that leads to some really nice characteristics. It means that when we download a cache record, we can see, do I need to download this locally, or do I already have this content? But it also works on the opposite side, where when someone's uploading something, you have two cache records that reference the same texture. We can potentially, like, if they reference the same texture, they will have the same attachment hash. So we'll only need to upload it once. We can deduplicate it. We know we don't need to replicate it, those kinds of things. So content addressing can be quite valuable in both like downloads and upload scenarios. So that's like the fundamental object that we store. And this sort of cached object itself, like the metadata about it, like the actual cache record, that will go into Scylla, while all of these other attachments goes into our blob storage. So Unreal Cloud ETC, it's an API that we run in Kubernetes in a bunch of different places. We run about 5 regions for Epic right now. You can see the world map there on the right, sort of highlighted where we have our different regions. So these web API servers, they just serve the content that people are requesting. And as I mentioned, like the metadata goes into Scylla, and then all of the blobs goes into S3, and we actually front that with like a local NVMe cache of like 7 terabytes. So that means that when you go to fetch the actual payload, we'll fetch that from an NVMe cache instead, typically. But that's not like large enough to fit our entire payload, our entire data set. So right now we store about 50 terabytes in S3 for this data. And it used to be said that that's lost access tract, so we will delete data that hasn't been accessed for a while. So 50 terabytes, that's the amount of data that we need in about 2 months for building our games. So this is quite a lot of data. And also it's worth noting that the 50 terabytes there, that's for one region, so it's times 5 in terms of the amount of data that we have to store in the system. So it's quite a lot of data. And then our region sizes will vary a little bit. Some of our smaller sizes have like 10 users working with them, so it's fairly small, but they're in some sort of some separate network where it's sort of hard for them, like they will have really bad experience if you try to go to another region. Perfect example is Australia. And then we have some other regions, like we have quite a lot of people in North America, so we have double regions there and so on. And I think like peak users is about, I think it's even more than 500, I think it's like 700 users in our most used region. So yeah, quite a lot of users sort of separated all around the world, really. So let's have a look at what the actual architecture looks like. You can see the Unreal Engine logo there on the left. That's supposed to be like the editor or some other case where someone needs to get hold of this content. And that will talk over HTTP to our web API, Unreal Cloud ETC. And what it will do is it will go to Scylla to fetch the metadata. In this case, like it's mostly resolving the cache key, right? So like I have this key, it's supposed to map to this object. Does it exist, or what is the object? So that's a request that we could do against Scylla. You can see the sort of thing there on the right. That's supposed to be another region. So you can see the lines between Scylla there. So Scylla will replicate data between each other, just as it always does. And we just let it do its work there, really. And then Scylla will give us back like, yeah, this is the cache key that you wanted. Here's the blob that you stored. So what we do is we actually take the cache key, the actual object that we store, and inline that into the Scylla database if it's below 64 kilobytes, which it typically is. So that's like the high level description of like, these fields that you saw. And that works really well. Honestly, we get like sub-millisecond responses for that most of the time. So that's really, really efficient. And then that will go back to the web API, and it will be able to determine, did people ask for other attachments? Should we send those as well, or do they want to fetch them later? If they do want those blobs, we'll go and check the local MME storage and then go to S3 to fetch the data that they need. And that can take, that will depend on the size of the asset and so on, how long that actually takes. One kind of weird thing that we do here is that, as I mentioned, like the lines between Scylla there, Scylla does its own replication. But for S3, we do not rely on S3 replication. Instead, we actually roll that ourselves. So whenever we write anything into the system, we will write a journal in Scylla where it says like, I wrote this this asset now, this key now got updated. So then people will know that it needs to get replicated. So we'll be following that in all of our other regions and just pulling data across as we need it. This actually means we do that quite aggressively. So it means that we actually replicate data quicker than what S3 would do out of the box with its built-in replication. And it also allows us to do like selective replication, only replicate certain things we need. So it ends up being quite valuable for us. But so, yeah, it works out quite well, even though it's sort of a bit of a funky setup. But yeah, we're quite happy with it. But so why did we decide to use Scylla then? And that answer, there's multiple reasons for us deciding to do that. I think the primary argument was cloud agnosticity. When we first built this as like a prototype, we used DynamoDB on AWS. Worked quite okay, but when we wanted to sort of be able to provide this to licensees, we decided that we wanted something that wasn't bound to a particular cloud provider. It might even be possible for one of our licensees to not even be on any cloud. It might be on completely on-premise. So having a solution that could just work anywhere, like Scylla, was quite key for us, honestly. But also, as I mentioned before, this is a fairly performance-sensitive workload, so it's important for us to get a response quickly. And Scylla's performance is just so much better than what we got out of Dynamo. And honestly, the cost was much better as well. So it was just everything just was in its favor, really. Initially, when we looked at databases, a geo-replicated database was a requirement for us, which was why we started with Dynamo and then went to Scylla. Honestly, we could probably, like as I mentioned, we do the blob replication ourselves. We could probably have built, replication ourselves using that as well. But the fact that we don't need to is just great. We get it out of the box. It's faster than anything we do. It works really well. It's just perfect. And then, yeah, I mean, the other potential drawback you could imagine would be the eventual consistency, right? But for us, because we have to replicate these really large payloads anyway, and that just takes time to physically move from one place to another, we have to build in the eventual consistency in the API anyway, so that doesn't really end up being a problem for us. I do think by normal standards, we run fairly small deployments. So we run in like multi-AC fashion, so we have 2 or 3 ACs in one region, and so that means 2 to 3 nodes of Scylla in one region. And we'll pick the node type based on the expected load, really. So right now we typically run i4x large on like our smaller regions, and 2x large in our larger regions, and those typically have more ACs as well. So that works really well, honestly. We started out with i3EN machines, but then we saw the blog post about i4i and moved to that as soon as we could. It's been really good. Highly recommend using that if you can on AWS. I think the biggest problem we had was the fact that i4i didn't exist everywhere in terms of like AWS offering. But we've recently migrated in like all the regions that we use to that. So yeah, it's been perfect. And yeah, number of requests, we see about 3,000 requests per second per node. So it's not like, I mean, it's not insignificant, but it's not like a huge load either. Interestingly enough, our load is relatively consistent over time. And that tends to be because a lot of the load is produced by our build farm. And the build farm is pretty much producing new cached assets 24/7, because there's pretty much always someone somewhere around the world that has changed something that results in a bunch of new data that needs to go into the system, right? So not a lot of ebb and flows in the system. It's a fairly high load. And even if there are like low periods of people submitting things, those are usually like, there will be things scheduled in the build farm to do like bigger work that might use unusual assets or something like that. So yeah, fairly consistent load for the entire system, I'd say. We've been using the system around Epic for a bit over a year. We use it for like all of our different projects. It's been working really well. So the next big step for us is getting this out to more licensees. Yeah, so there's definitely future work we can do. We've found that this inlining of blobs into Scylla is actually working really well. It gives us, a blob within a millisecond usually when they're really small. So that just seems like a perfect opportunity to consider putting like our small blobs into Scylla instead of putting those into S3, since S3 isn't particularly fast with small blobs. There's a trade-off there. I mean, S3 storage is quite cheap. The storage that we run for Scylla isn't really, so there's some sort of trade-off where it's unclear when exactly it's worth doing that. But it's an area that we definitely want to consider, especially as that would let us fetch these small things really quickly, which could be really valuable. Then another big thing we're looking at is working with licensees to get this set up. for them. And we work quite closely with a lot of Microsoft studios, and they're obviously running on Azure. So one thing that we want to do is, get this. We've been doing improvements to Unreal Cloud DDC on Azure, and they're currently using Cosmos DB as their database there, just using like Cassandra API. And we're seeing, the performance isn't as good as what we see out of Scylla, and the cost isn't as great either. So we're trying to get the project going where we try running ScyllaDB as well and sort of can compare that. It's quite hard to compare these numbers between different games because they're just so like they change much depending on what kind of content you have and so on. So it's a bit hard to give like a fair comparison. But so that's why we want to try and get something set up with Scylla on Azure. And then, there's performance improvements we can do both to the API and stuff like that. We also gotten some really good feedback from the Scylla guys on how we could change some of our tables and so on to sort of, just generally improve the performance. That's definitely something that we're going to look at. And this storage, we've talked about this, is like a caching system right now for DDC. It's actually built as like a general storage, like structured storage system. And that's on purpose because we think that there are multiple workloads that we could put into the system that we currently do not. So that's a future work that we're going to do, is just extending this into way more workloads. For game asset type stuff for sure, but just other things than just the pure cache. Right, so before I go, I just wanted to mention that Unreal Engine is source available. So if you're curious about how we're using Scylla or just generally how to make games, you can sign up on our GitHub. You can go to our GitHub and you'll find the information you need, how to create an account and so on. It's free, and then you can look at our source code, figure out what you want to do with that, build any kind of games you want to. So enjoy. And thank you for listening to me, and here's my contact information if you want to stay in touch. See you around.